As Ray just mentioned, the last part of the Rochester Mineralogical Symposium this year is comprised of a series of 3 short lectures on crystallography for mineral collectors. The first will deal with crystallographic concepts, such as the crystal systems, plus additional material by myself, John Rakovan. The second presentation will be by Ruthie Rutherford, also from Miami University. And she'll be talking about Miller indices, the numbers that we associate with crystal faces. And Pete Richards will finish the program looking at crystal forms, which are defined specifically as sets of symmetrically equivalent crystal faces, and essentially are the shapes that crystal faces create when they're found on a crystal specimen. The concepts that we are going to be going through in these 3 presentations will start with symmetry, one of the fundamental properties of all crystals, and then crystallographic concepts associated with symmetry that are useful in identifying and looking at crystal shapes and understanding what they are the result of. This will include the crystallographic axes, oftentimes referred to as X, Y, and Z, or A, B, and C. The crystal systems, isometric through triclinic, which are defined by the presence and absence of certain types of symmetry. The concept of the crystal lattice, a representation of the repetition of the atomic structure. The unit cell, which is the smallest unit within a crystal lattice or crystal structure. Again, Miller indices, which are the numbers that we use to assign to crystal faces. And crystal forms, which are the sets of symmetrically equivalent crystal faces that lead to the shapes that we see within crystals. So let's start with the origin of the term crystal and our understanding of what crystals are today. The word crystal derives from the ancient Greek word kristallos, meaning ice. And it was applied to beautifully faceted quartz crystals like this one here, which were thought to be ice that had frozen so cold that it could never melt. So our first use of the term crystal was to describe objects with a specific morphology, such as the quartz crystal we see here. Now today, and since the advent of X-ray crystallography in 1912, where we could start to see the internal arrangement of atoms within crystals, we have a new definition for what a crystal actually is. The external morphology is purely a reflection of the internal atomic order and is also the result of how crystals grow. Our definition of a crystal today, however, is a solid material that has a 3-dimensionally regular arrangement or periodicity of the atomic structure. And that's how we can think of crystals, and all of the concepts that we're going to apply today can be derived from or applied to the types of features that we see in that atomic structure. This is a high-resolution transmission electron microscopy image showing a apatite nanocrystal. You can see the hexagonal shape there. And we're actually magnifying this crystal to a scale where we can actually start to see the atomic structure. You can see the repeating lines, which are actually the edges of planes of atoms that run periodically throughout the crystal here. We'll also notice that those planes, or the orientation of those planes, is parallel to the orientation of planes which define the exterior morphology. In other words, crystal faces are parallel to planes of atoms within crystal structures. Just to note, the scale bar here is 5 nanometers. So we're down at the realm of being able to see individual atoms. And a little bit later on, we're going to talk about the unit cell. Within this high resolution TEM image, we can actually see the individual units, what look like diamonds here, which we define as the unit cell for apatite. Now, the exterior morphology of crystals, as I just mentioned, is a reflection of the interior symmetry that is the result of the periodicity of atoms throughout the crystal, the defining characteristic of a crystal. And so crystallographers have come up with different ways of describing that repeating nature in the pattern of the atomic arrangement or the repeating nature in the pattern of crystal faces. And we define this by different types of symmetry elements and the operations of those symmetry elements. And I want to show you just a few examples of that. So this is a forsterite crystal from Sri Lanka. We can take an idealized model of that crystal and start looking at the symmetry within it. The first type of symmetry element that I want to describe is known as a mirror plane. And of course, there's no true mirror plane within this crystal. I've drawn one here. Symmetry elements are concepts. They are constructs to help us understand or describe symmetry. What we actually see in symmetry is the repetition throughout three-dimensional space of both the pattern of the crystal, the shape of the crystal, or the atomic arrangement. In crystallography, we define symmetry elements as objects. So in this case, we're defining a symmetry element that we're calling a mirror plane. And that mirror plane would reside, for example, in this position and orientation within the crystal. We say that the operation of a mirror plane is simply reflection, just like a mirror reflects an image. And then in this context, we can think of the left side of the crystal being the mirror image of the right side of the crystal. And so that repetition, the mirror imaging of the shape of the left and right hand side, can be described by the presence of a mirror plane here. Another type of symmetry element is an axis of rotation, and there are axes of different fold rotations. In crystallography, we can have two-fold, three-fold, four-fold, and six-fold axes of rotation. And let's apply the concept of a two-fold axis of rotation, which exists within this crystal shape here. Imagine we have an axis that cuts through the center of the crystal in this particular position and orientation. And you can imagine that if I rotate this crystal 180 degrees about this axis, it will repeat itself in space. In other words, the shape will be exactly the same. We won't be able to tell it from its original position. Now, to get back to the original position, we could rotate a second time, and that's why we call this a two-fold axis of rotation. So we describe this symmetry element, again, as a two-fold axis of rotation, or an axis of two-fold rotation. And the operation of that is rotation about that axis by 180 degrees. Now, if you're astute, you'll notice that there are other mirror planes and other two-fold axes of rotation in the shape of this particular crystal. I've just shown two of them, one of each. However, there's another two-fold that sits in this orientation. Again, I could rotate the crystal about this axis by 180 degrees, and it would repeat in space. If we look for all of the symmetry elements and draw them in, we actually have three axes of two-fold rotation and three mirror planes, and all of those now are drawn or superimposed on this crystal shape. The symmetry that we see, that we're describing by these axes of rotation and these planes, mirror planes, and there are other types of symmetry that I'm not going to get into here. For example, a center of symmetry. These exist as the result of the repetition of the atomic arrangement and then the reflection of that in the crystal shape. And so symmetry is what is real, it exists, it's observable. All of the other concepts that we're going to describe now, crystallographic axes, lattices, etc., are constructs to help us describe and think about crystals. And we want to base these concepts or these constructs on real observable features, such as symmetry. In other words, we use the symmetry that we see within crystals to define where we are going to put our crystallographic axes, where we choose our lattice and unit cell, and then how we define the orientation of crystal faces, which will be the talk on Miller indices that will come next. In this particular crystal, which by the symmetry present turns out to be orthorhombic, we define the crystallographic axes, X, Y, and Z, as being parallel to the twofold axes. Again, we use the symmetry to define where the crystallographic axes are. Once we have those axes, we can talk about different features relative to them. For example, the twofold, which is shown by the blue symbol here, is parallel to the x-axis, and that twofold is perpendicular to both the z and the y-axis. Officially, the crystallographic axes are labeled X, Y, and Z, and as we'll learn in just a moment, the lattice repeat along those axes are given the dimensions A, B, and C. However, since the direction of repeat is always parallel to the axis, we oftentimes will use A, B, and C to refer to the axes themselves. So X, Y, and Z are sometimes referred to as A, B, and C. This is another crystal shape on the right here, showing all of the different symmetry elements that we see within the shape. Now, it's a simple shape. It's the shape of a cube. And in this case, we have many, many more symmetry elements. We have twofold axes of rotation, like we saw in the previous crystal. We also have fourfold axes of rotation. There are 3 of those here. And we have threefold axes of rotation and many, many more mirror planes. Now, all of the symmetry we see in that external form also exists in the atomic structure. Remember, the external form is a reflection of the symmetry that actually occurs by the repetition of atoms in 3-dimensional space, that atomic arrangement. In this particular case, we define the X, Y, and Z axis as being parallel to the fourfold axes of symmetry, and I show their orientation and position with respect to the crystal structure here. Now, a little bit later on, we will see that this outlined area with the red bars is what is called the unit cell. It's the smallest unit of repeat of the crystal structure. In other words, you can think of this as the building block, and then we can just repeat that to the left and to the right, up and down and back and forwards in 3 dimensions and build up an entire crystal structure. Now, I had mentioned the crystal systems earlier. Many of you have heard of the terms isometric, tetragonal, hexagonal, trigonal, orthorhombic, monoclinic, and triclinic. Those are the names of the different crystal systems. Now, as we've already mentioned, we're using the observable features of crystals to define all of these different crystallographic concepts, including the crystal systems. And the features that we can observe are the types of symmetry that are present or not present. And we use these to define the different crystal systems. In the case of the isometric system, the defining characteristic is the presence of 4 axes of threefold rotation. In the tetragonal, it's the presence of 1 axis of fourfold rotation. In the hexagonal, it's the presence of 1 axis of sixfold rotation. In the trigonal, it's the presence of 1 axis of threefold rotation. Now, in the isometric, you can have axes of threefold rotation also, but if there's only 1, it's going to be trigonal. If there's more than 1, there can only be 4, and it's isometric. The orthorhombic is defined by 3 axes of order 2, and I won't define exactly what an order is here, but for example, 3 axes of twofold rotation would be orthorhombic. The monoclinic is defined by 1 axis of order 2, for example, a single axis of twofold rotation. And finally, the triclinic is defined as having no rotational symmetry elements present. Now, there's one type of symmetry element that can exist in the triclinic. We haven't discussed it, but you may be familiar with the center of symmetry. And so triclinic crystals can have no symmetry at all, or the presence of only a center of symmetry. So that's what defines the crystal systems. In just a moment, we will look at the characteristics of those systems in an aspect that is very oftentimes confused with being a defining characteristic. Now, axes of rotation and mirror planes are two types of symmetry that we see in the external morphology and in the internal structure of crystals. Another type of symmetry which is not observable in the external morphology but is present when looking at the crystal structure is translational symmetry. And the concept of the crystallographic lattice is simply a representation of what that translational symmetry is. So let's use this crystal structure. This is the structure of olivine, that forsterite crystal that we started with, but now we're down on the atomic level. And I've drawn this perpendicular to the C crystallographic axis. So we've got the X running vertically and the Y-axis running from left to right. And again, we would define the orientation of those axes based on the symmetry, mirror planes, and rotational axes that are present within this crystal structure. In the case of translational symmetry, this represents how atoms repeat in space going along the three dimensions X, Y, and Z. So let's start with this green atom up here. That could be, that is the position in the structure where either magnesium or iron resides. And we'll mark that with a red dot. And let's move now, or translate along the X direction to the next position that it repeats. And we find that we have a green atom in that position there. It's identical. And so that's an identipoint. Those 2 points shown in red are identical. Now I can do the same thing along the Y crystallographic direction. And if I do that, that's my translation direction and vector or amount. And I repeat that object in this position as well. So this is the concept of looking at translation in 2 dimensions. And of course, in the the Z direction, we could do the same thing. If I do this and continue along the X, Y, and Z direction, I will end up marking all of the equivalent points from my starting point, everything that's equivalent to that starting green atom, throughout the crystal structure. And it's this 3-dimensional, shown here as 2-dimensional, lattice of identipoints which defines the lattice of the crystal. In other words, it's just showing the periodicity of the structure. So here I have the lattice drawn in red dots superimposed on the crystal structure. If I want to think just about the lattice, I can remove the crystal structure. And this again shows us the repetition within that crystal structure, what we call the lattice. The repeat dimension along the X direction is defined by the variable A. And of course, since the vector for A is always parallel to X, we can also use the term X-axis as well as, A-axis as well as X-axis. But officially, or precisely, A is a repeat dimension. In other words, it has a vector to it, both direction and magnitude. The repeat dimension in the Y direction is given the symbol B, and the repeat dimension in the Z direction is given the symbol C. So A, B, and C are the units of repetition, usually expressed in lengths of angstroms, along the X, Y, and Z crystallographic axes. Now you can see within this pattern, you can define a small tile or unit. In this case, this is the 2-dimensional projection of that repeating unit. And this is what we call the unit cell. In other words, you can think of starting with simply this unit cell and then developing the entire lattice by simply tessellating or translating and repeating that unit cell along X, Y, and Z. This is a diagram to show the general defining characteristics of all unit cells, no matter which crystal system we're in. All unit cells will be 6-sided parallelepipeds. That is, they will have 8 corners. The edge lengths of those unit cells are the repeat dimensions of our lattice. So they are A, B, and C along the X, Y, and Z crystallographic axes. And finally, the angles between those axes are defined as alpha, beta, and gamma. Now those angles and these edge lengths are constrained by the symmetry that's present within the crystal structure. And next I want to show you what those constraints are. This is very familiar to many people that have looked at the crystal systems, but they oftentimes confuse these constraints with being the defining characteristics of the crystal system, which they're not. So the symmetry that exists within the crystal structure, and we're not showing the symmetry now. We can define the symmetry of the unit cell shape, but that's different than the actual symmetry within the crystal structure. The symmetry that exists within the crystal structure places constraints on what the unit cell size and shape will be. In the case of the isometric system, what is the defining characteristic of isometric, also called cubic, which I've written here? So these unit cell metrics, A is equal to B is equal to C, alpha, beta, gamma are all 90 degrees. That actually does not define isometric. That is a result of the presence of symmetry and the fact that that symmetry constrains these things to be equal to what I've shown here. The defining characteristic, as we've learned before, is based on the symmetry present, and it's the presence of 4 axes of threefold rotation. If you have those, it constrains A and B and C to be equivalent and all of the interaxial angles to be 90 degrees. And so the shape of the unit cell is a simple cube. In the tetragonal system, A and B are equivalent. They have to be by symmetry, but C is not equal to A and B. This symbol in crystallography, not equal to, actually is thought of in a different way. Mathematically, when we say something is not equal to, it is truly not equal to it. But in the case of crystallography, we mean that it's not constrained to be equal. In other words, there may be tetragonal crystals based on symmetry where A, B, and C are actually all equivalent. But the C does not have to be, that is, it's not constrained to be equivalent to A and B. The symmetry in the tetragonal does constrain alpha, beta, and gamma to be 90 degrees. And likewise, I won't read through all of these, but you can see the constraints. As we lower the symmetry, we also lower the constraints. So in the orthorhombic case, none of the edges of the unit cell, in other words, none of the repeat dimensions in X, Y, and Z are constrained to be the same. In the hexagonal, things are a little bit different because we've got some angles that are defined at 120 degrees. Okay, so alpha and beta are constrained to be 90 and gamma is constrained to be 120. Like the tetragonal, C does not have to be equal to A and B, but A is constrained to be equal to B. In the monoclinic, all 3 dimensions can be different. Alpha and beta are 90 degrees, but gamma is not constrained to be. And finally, in the triclinic, which is defined by the absence of any axes of rotation, there are essentially no constraints. A and B and C can be different. Alpha, beta, and gamma can all be different and can all be something other than 90 degrees. And so the triclinic has the least amount of symmetry and the least constraints on the unit cell. Now to finish up here, and before we move on to Miller indices with Ruthie, I want to show a little more about the hexagonal system because it behaves a little bit differently because of the symmetry. So the topology of lattice points is shown in the unit cell here. Let me show you a hexagonal lattice looking down the z-axis. Okay, so here's the hexagonal lattice in terms of the lattice points. We can see the shape of a hexagon within this lattice, and we might say that this is the shape of the unit cell. But based on symmetry, we can actually divide this hexagonal unit cell into 3 equal parts. In other words, we say that it's triply primitive. And that actually is the unit cell that we define for the hexagonal system. Again, it's in 3 dimensions. It will be a 6-sided parallelepiped. We define the x-axis as being in this orientation, the y-axis, which is in this orientation. Because they're equivalent by symmetry, we can call this one x1 and this one x2. And because of that symmetry, there's actually a 3rd crystallographic axis perpendicular to the z-axis. The last slide here I'm going to show you is the axial system for the hexagonal. So I've got z oriented in the left here, left image vertically, and you'll see the x1 axis, the x2 axis, and the horizontal. x3 is a 3rd x-axis. That is simply the result of symmetry. We don't need to use 4 axes of dimension for 3-dimensional space, but it's present because of the symmetry. If we were to look down the z-axis, this is the pattern that we would see. This hexagonal array of x-axes, x1, x2, and x3. So the next time you see a hexagonal crystal, like one of these apatites, if you look down and see the hexagonal shape, you know that's where the z-axis is oriented. And the 3 x-axes will be oriented in the plane perpendicular to that. These concepts of crystallographic axes in the lattice are essential for understanding Miller indices and crystal forms. And I will now defer to Ruthie Rutherford from Miami University to finish up our discussion of, or to continue our discussion of crystallography and to teach how Miller indices are determined.